Okay, we have here the integral from 1 to 10 of the floor function of x all cubed dx. And this was my attempt to write a problem for an integration bee. Just an easy one though, I didn't really put too much into it, of course. But still, I do think this is pretty nice. So what I want to do is, the usual thing we do on the floor function is it's nice if we split the bounds up where it's separated by 1. So like, for example, going from 1 to 2, the reason to do this is it's going to reduce this to an integer value. I mean, I guess the floor function always resolves to an integer value, but doing it this way, it's going to work out nice. So between 1 and 2, the floor is going to round us down. When our x values are always between 1 and 2, the floor is going to round us down to 1. So this actually just becomes 1 cubed. And then for the next one, what's happening, we're going 2 to 3. Same thing, between 2 and 3, the floor rounds us down to 2, and we have 2 cubed. And so this is just going to keep going. We're going to have, over here, we're going to have a 3 cubed. And this will just go all the way to this last one, which is going to be from 9 to 10. Floor is going to round us down to the 9 value. So if we just generalize any one of these, it's going to be something like an integral from n to n plus 1, where we always get rounded down to the lower bound. Notice this value is always the same. So it's going to round us down to n cubed. But n is just a constant, or n cubed is just a constant. So then we're just integrating 1. And the nice thing about doing the bounds this way is this thing, it always evaluates to 1, because what's going to happen, we'll have the constant out front, but then this is just going to be x from n plus 1, from n to n plus 1. The difference is 1, so this piece is just 1. So really what we can do is write this thing as a sum starting at 1. This is going to be like our first n value. So going from 1, not to 10, but to 9. That's going to be our last lower bound. So we want to go from 1 to 9 of just n cubed. And then for this thing, we can just use a formula for the first n natural numbers cubed. And I don't really like to remember that formula. What I like to remember instead is something a little bit different. What we can say about this, let's say we have the sum of, we'll just do the same thing. We'll do n cubed from 1 to our upper limit we'll call k. What we can do is we can relate this to a simpler sum, this thing, just the sum of the first n natural numbers from 1 to k. But it's not quite this, it's actually this thing squared, which is going to be our value for the first k cubes. But the reason to use this is we got a well-known formula for this thing. This is actually just going to be k times k plus 1 over 2, but we've got the whole thing squared. So coming back to our problem, all I need to do is use this formula where k is going to be 9. So the numerator is going to be 9 times 10. This is over 2, all squared. What we have here is 90 over 2, or 45 squared. So for my final solution to this, we have just 20, 25, and that's it. Okay, there you go. Thanks everyone for watching. Have a good day.